Good morning and welcome to today's session. Today we are going to discuss Bayesian models, the grand gateway to the kingdom of probabilistic machine learning. Our goal is to collect full information of the model, whether it is a machine learning model or a statistical model. The agenda of this session are basic terms and Bayes theorem, posterior as a pattern of full information, comparison between Bayesian model and frequentistic model, and finally some applications. The basic terms in Bayesian model. In Bayesian framework, probability is a measure of uncertainty, not a chance. Most useful properties of probabilities in this model are the famous multiplication theorem and addition theorem. Probability for A and B is equal to P of A given B into P of B. P of A or B is equal to P of A plus P of B minus P of A and B. It is known as addition theorem. Now we are going to state Bayes theorem formally. Let capital A and capital B are two events such that information related to B is known. That means information related to the second event B is known. In this situation, A is happened. Now the effect distribution of A on B is as P of B given A is equal to P of A given B into P of A divided by P of A. This is called the Bayes theorem. In this context, P of B is known as the prior information or belief or prior distribution. P of A is called the evidence. The denominator is known as the evidence. It is actually a marginal distribution. P of A given B, this one, that is called the likelihood distribution. P of B given A, that is our left hand side, it is known as the posterior distribution. We are focused on this posterior distribution. Mathematically, this is just a probability formula, but in application level, this P of B given A is the measure of information on this B under this evidence A. That is why it is called the effect distribution of A on B. What is the effect of this evidence on this B? That is captured in P of B given A. That is why it is called the full model information, full probabilistic model information, whether it is a machine learning model or a statistical model. Now we reinterpret Bayes theorem for our machine learning context. Let theta be the parameter of a population and D is a sample with this parameter. Now the parameter distribution based on this sample is P of theta given D is equal to P of D given theta into P of theta by P of D. So D is our data, that is a sample taken from the entire population. Theta is the parameter calculated from the sample. Now we are going to identify what is the effect on this parameter theta by this taken sample D. That's all. That is why it is called effect distribution. Any model make use of the Bayes probability is called a Bayesian model. That is the core of today's session. What is a Bayes model? A Bayes model is nothing but any model, whether it is a machine learning model, deep learning model or a mere statistical model that make use of Bayesian theorem in probability is called a Bayes model. That is the definition of Bayes model. Then there is a black humor related to people who are believing in Bayes theorem. It is very interesting. Who is a Bayesian? That is defined by this humor. A Bayesian is one who vaguely expecting a horse and catching a glimpse of a donkey strongly believes he has seen a mule. Even though it is a humor that criticizes the Bayesian beliefs, but I consider it as an encouragement to explain the Bayes theorem more deeply. Now we just focused on the different term, the Bayesian who is believed in Bayes theorem. The person who vaguely expecting a horse. This vaguely expecting horse is actually prior distribution. From our reading and from the information that we heard, we form a mental picture about horse. At this time, you just believe that there is no photograph or video related to horse. We don't see anything like that, because we think that we are living in a stone age. There is no visual media, there is no social media like that, so we cannot capture the horse picture, but writing is there. So in the literature we know what is the horse, what are the characteristics, so we form a mental picture based on that. That is our prior knowledge or belief. So vaguely expecting a horse is actually our prior distribution or belief distribution. Then what happened? He catch the glimpse of a donkey. He just saw a donkey. Then naturally the mental picture come into the scene. Then he misunderstood it is a mule. From his speculations and from his analysis, he come to the conclusion that it is a mule. This last one, he has seen a mule, he strongly believes he has seen a mule, is our posterior distribution. Now I told you vaguely expecting a horse is simply a prior knowledge or belief. Now catching a glimpse of donkey is our likelihood distribution. That glimpse create association or link to the new information. That is likelihood, that creates the likelihood. We can explain this prior and likelihood in a more practical situation. Some people boast that they are belong to this family, their family has these much things, her grandfather was the minister of Kerala, like that. All these are beliefs. All these are belief distribution or prior distribution. That's all. This is taken from the past. Now next is, for example, a person sitting in the home now and he try to plan a new business tour. He will start tomorrow morning at 8 o'clock from our Kochi airport and go to Philadelphia, then take his breakfast from there, and he will go to next place like that, and evening itself he come back to India and he come to his room. All these are his plans, his expectations. It is possible, it is absolutely possible if it is not a lockdown period. See, it is a lockdown period. All these are his expectations or likelihood, the possibilities that he can do as a businessman. But what happened? He forget about the prior knowledge. The prior knowledge is that in COVID-19 circumstances, we are in the lockdown. If he goes to any neighboring countries, he will be there in quarantine. Then he come back to India, again he will be in quarantine. Then how can he come to his home today itself or tomorrow itself? Is it possible? No. So he just forget about the prior knowledge, the prior belief distribution. He planned like this. So likelihood distribution is like this. Under the present circumstances, we plan something. We form the possibility distribution based on the current knowledge. That's all. This approach is known as the frequentistic approach. The people who are believing frequentistic approach are just look into the likelihood distribution. The probability distribution and probability theory, what we have learned in all our classes, is just frequentistic distribution. I am not talking about the probability distributions like binomial, Poisson, beta, etc. I am talking about the classical probability calculation methods. How we calculate probability? Probability is considered as the favorable odds. The favorable odds. For example, when I start my journey from RIT Kottayam, see the college in a hilly area, I start suppose I am in the civil department. For example, civil department is in the southeast part of the campus. Then I start walking from the top floor, then come to the main road. It is very steep, and so there is a probability to fall. I repeat this experiment 5 times. Out of 5 times, I fell down in 2 situations or in 2 cases. Then what is the probability to fall down? Number of favorable odds is 2. Total is 5. So 2 by 5. So we calculate the probability based on frequencies. Frequency by total. Or it is a proportion. The proportion for the favorable odd. Like that. When we multiply this proportion by 100, we got the percentage. When we geometrically explain this idea, it is simply area under the distribution curve. That's all. Then I will give you another instance. What is the probability that in the next election, Narendra Modi ji will be the next Prime Minister? I repeat, what is the probability that in the next election, Pradhan Mantri Narendra Modi ji will be the next Prime Minister? Can you do the random experiment? Oh, suppose as you are a frequentistic, you just call the election commissioner, sir, we are going to calculate the probability for Narendra Modi ji as a Prime Minister in the next election. So you should declare election to 50 elections. Then we will repeat the elections and try to calculate the probability. Is it possible? Theoretically it is possible. No doubt. We can call for election 50 times. Can you imagine the expense for one election? That the total growth of the nation will be very inversely affected by this decision, isn't it? So we cannot use frequentistic approach there. But we know what is the probability, because we have the previous knowledge and also the likelihood knowledge. We bring this together, we mix it together and form the probability distribution of the probability for Narendra Modi ji next time. In Kerala context, it is very easy because we know 50-50 chance every time from our previous information or previous knowledge. In that case, the prior knowledge give more importance, more weightage. So anyway, a person with higher level of intelligence will always use both the prior knowledge and also the likelihood knowledge. Both the prior distribution, that is belief distribution, and also the likelihood function or likelihood distribution. Bring this together. Under the evidence, he creates the posterior distribution. Based on the posterior probability, he will take action. That is a successful man's theory. He considers the past, considers the present, and he based on this and also considers the evidence, he will start next plan. That is his next jump. All the successful people are doing like this. They are Bayesians, not frequentistic. If they are frequentistic, they just stick on to current situation. They are not going to next step, next level. Now look into the cinema. Suppose we brand a particular cinema as a very surprise thriller, a surprise thriller movie. What happened in a surprise thriller movie? Suppose it is an investigation story. In the story, there are lot of prior distributions will be created, the situations, past and flashbacks, etc. Then the director or the writer create a situation for this likelihood of some murder or some activities or some action. It's a likelihood. Then they create the posterior distribution, the reason for that murder, the who is behind that murder, like that. Who is behind that particular murder? It creates a distribution. Then he tried to unravel the least probable thing first. Then next highest, and finally the twist happened. At that particular point, he revealed the highest probability event. That will be the climax. If we start with the highest probability event at the first, we will lose the thread. The suspense will be broken. That's all. So this is the idea. In another case, suppose you are interested in detective stories like Arthur Conan Doyle, our Sherlock Holmes stories. How the Doyle explained the stories, it's very nice. Sherlock Holmes goes through the different area and collect information, and that is to create the prior distribution. Then he go to the place at which the particular incident happened, then collect evidence, that creates likelihood. Based on this prior knowledge and likelihood, he create posterior distribution. He unravel the truth behind that particular incident. That's all. How the police force conduct investigation? They do the same thing. They collect the past information, the prior information about notorious criminals. Then go to the place, collect the evidence, all the evidence, and create some likelihoods. Then mix these two and create posterior distribution. Who is behind this? In Malayalam, there is a very nice proverb, Chattadu Kijaganangil Konnadu Bhiman. The same thing. That is a wonderful example of Bayes Theorem. So Bayes Theorem is behind a very successful, brilliant man. If you want to be a successful, brilliant man, there is no doubt you will be a Bayesian. You can use the Bayesian concept everywhere. Remember these two things: the prior distribution, likelihood distribution. If they are very bad, that is not good, in that case you come to this wrong decision or wrong distribution. So the prior knowledge should be strong, prior distribution should be apt to the situation. Also the likelihood, our speculations, that should also be strong based on the evidence. If both these distribution are okay, then the posterior distribution will be better than any other decision, and it will contain all the information related to the model, no doubt. But one thing, it is not easy to collect all the prior information from the data. But unfortunately, the computational ability will increases and the computers become more powerful, and so we can collect more data. Availability of data now increases because data is like oil now. It's most expensive, at the same time availability is more and more because of the invention of technology in the sample collection. We collect samples in all possible ways. That is the reason. Now based on all these samples, collect as much as prior information, then create the prior distribution. That is more important. So data collection is very important. Quality data collection is important. Then only we get the correct prior distribution. Then likelihood. What are the reasons behind this particular event? That likelihood distribution should be generated based on the evidence. That is very important. Under these two conditions, what happens? We create a good posterior distribution. In such situations, we can use our algorithm. But that algorithm, MCMC algorithm, sampling algorithm, will be very much helpful to collect posterior information from minimum number of data. Okay, now we come to the use cases. Generative models. That means we are going to generate new models from the existing model. That is necessary. We cannot stuck on the present. We have to go to the next level. So generative models can be created with help of posterior distributions from Bayes theorem. Then weather alarm systems. So we are using everywhere the weather system, predictors, radars, sonars. All these are sensors. They collect information, and we have also the prior information. Using the present information and prior information, we are going to take predictions. Okay, so the weather alarm system become more powerful when we apply the posterior distribution. Then probabilistic models for AI. In artificial intelligence, especially in machine learning, what we are doing, we are trying to predict fixed values of parameters. For example, we consider the simple linear regression. In linear regression, y is equal to some a plus bx, it's a single straight line with only one variable x. but two parameters A and B, where A is the fixed value, that is called the intercept, and B defines the slope of the line, how it incline to the positive x-axis. Okay, then we try to form a model. There are two ways. One is purely statistical. We create normal equations for this y is equal to ax plus a plus bx, then solve the normal equations, we directly get a and b. But if the sample size is very large, we have more information related to x, the solving of this equation become very difficult, because calculating this mathematical formula, the mean and variance, is very difficult. Such situations we use iterative method, especially in computers we are using iterative method, gradient descent approach. Then we start with an initial value, update the value iteratively until there is no much change in these variables a and b will happen. Then we stop. That is called the stopping condition. Okay, in that case also we think about fixed values of a and b. Then what is new in Bayesian model? We are going to derive a distribution for a and b. That's the difference. The last two sessions we have discussed this. What is happening here? The difference is values changes to distribution. The fixed values of parameters become probability distribution. That's the thing. The probability for a and b. If probability is very high, we choose that parameter. If probability is very low, we discard that, like that. So the probabilistic model change the full scenario of machine learning, and so it will improve the quality of artificial intelligence. We move to the general artificial intelligence with the help of this probabilistic approach, especially the Bayesian approach. Okay, the loss functions in posterior predictive models. We can use this Bayes theorem as the loss function. In many situations, even in the expectation maximization algorithm, in some versions we use this Bayes distribution. At least we use the posterior probability from Bayes. See that in expectation maximization, I think you can recollect that the expectation maximization case, it is actually a probability function in log likelihood. Then what is the prior distribution? That prior distribution is actually the Bayesian distribution, the posterior distribution from the joint distribution of latent variable and our observed variable. That is the present situation, the evidence situation. That is a posterior distribution. So in more and more cases we can see the impact of Bayesian distribution, or in another sense the posterior distribution. We can interchangeably use the term posterior and Bayesian. Whenever we use the posterior distribution, the Bayesian distribution will come there. Whenever we use Bayesian distribution, it will become a Bayesian model. Okay, epidemic or pandemic analytics. It's a very nice thing. In this coronavirus attack or COVID-19 scenario, what we are currently doing, there are some population statistics and also pandemic and epidemic analysis, like SRI model, susceptible, infected and recovered model, SIR. These model make use of pure probabilistic approach. That means we try to fit a linear trend, then we also try a log linear trend, then we mix these two knowledge, then predict what should be the rate of death in coming weeks, or at what point or after how many days this impact of coronavirus become maximum, like that. We can calculate that. That is a routine epidemic analysis in our health system. If we incorporate the posterior distribution, we have lot of information related to the spread of corona now. We can make use of this, and so we have the prior distribution, and also we got the prior information from other countries also. We can make use of it and create probability distribution as prior distribution. Then the likelihood generated from our own environment, especially Kerala. Kerala is very much thickly populated. then likelihood is more high. That likelihood can be calculated based on the density of density in our population statistics. Bring this together, we create a posterior distribution. Use that posterior distribution to generate this linear or logistic model that will give you more information or more reliable information than our conventional statistical model. It is not a new thing. Theoretically, this Bayes theorem is there, but we cannot use it because of the computational complexity. But now things changes. We have good computational system, numerical system, even the probabilistic programming languages. We can make use of them to develop new models, new posterior models, two Bayesian models. That will happen in coming days, no doubt. Next is population models. The population models are based on only census. We simply make use of our statistical tools like mean, variance, etc., and some factor analysis and also some p-value system. We can change it. We can successfully change it with the help of Bayesian models. These are some use cases. Now, the important takeaway of this lesson, as it is an introductory lesson to the Bayesian models, we explain a lot of things. We try to connect the present situations or our own real life with the help of Bayesian models. Now, the important takeaways are here. Models used Bayes posterior is called a Bayesian model. That is a very important definition from here. Bayesian models provide probability distribution for parameters, not constant values. That is an important difference between our frequentistic approach and our Bayesian approach. The Bayesian approach is also known as probabilistic approach. In probabilistic approach, we are not thinking about the constant values of parameters. We try to find probability distribution for these parameters. Okay. Bayesian models provide better inferences because it perceives more information about the current system under the evidence and also the prior information with the help of likelihood, so it can capture more information, no doubt. So the inference is more qualitative. Using Bayesian probability, we can transform any ML model to probabilistic model. This is the main thing you have to keep in mind. We are transforming our existing models, whether it is an ordinary machine learning model or a deep learning model with some parameters. We change the fixed values of parameters to probability distribution, then that model will become probabilistic model. That's all. So probabilistic machine learning is not a new thing. We change our existing system into a higher level. We elevate our existing system into a higher level with the knowledge of probability, more clearly with the knowledge of posterior probability. So finally we can conclude that it is the gateway to the probabilistic machine learning and Bayesian data science. So Bayes model are nothing but those models which make use of Bayes posterior probability, and it is the gateway to probabilistic machine learning and Bayesian data science. If you are very much interested in data science, it is the best time to think about probabilistic machine learning. There are a lot of work actually progressing in this area of probabilistic data analysis. Okay, thank you very much for the patient listening. In future lessons, we will discuss about more deep details about Bayesian models, sequential Bayesian models, and also the hierarchical Bayesian models, and some important probabilistic programming languages are there. The Fortran we can use it, the MATLAB we can use it, but we are currently using Python and R for our machine learning science course. So it is better to use some Python libraries and also practice some basics of probabilistic programming with the help of Python. We will do it in the coming classes. Thank you.